All right, so in last week module, we talked about, we ended up talking about linear combinations, right? So given just a set of vectors, v1, v2, v3, etc. to vn, okay? So this is a finite set of vectors. Right? We want to we define a linear combination to be a sum of these vectors with a choice of scalars, right? And when I say scalars, I'm talking about real numbers. That's where our scalars come from. So some set of real numbers. So this is basic definition of just a linear combination. Okay. Now, what we're set out to do, so we just defined them and we started hinting at them during our class work of the next two topics that we're going to focus on here. Right now, what I want to ask myself here is given a set of vectors, right, like a finite set, and these are the vectors, uh, what vectors can these build is a question I may want to ask myself. Oh my goodness. What vectors can these build? And another question I want to ask myself are any of these vectors unnecessary? Okay. So those are the major questions we're going to ask ourselves over the next two sections. All right. Now, let's start when I say what vectors can these build. Right, let's kind of take a look at some geometric examples here. So we can kind of start building an intuition here as to what it is that we're asking here. All right, so let's say here, so I'm going to switch over here. So what we're seeing here is a vector u, right? And you see here, vector u is defined as 1, 2, right? And I have vector v as well. Okay, now if I type in any linear combination of u and v's, let's say 3u minus 2v, right? Or let's say here, plus, okay, and then you could see what that does, right? So it looks like, right, all of the vectors of any linear combination here, right? And let's try a few other values here. Right, so as we could see here, any kind of linear combination, or the few examples that I've inputted here, have just been vectors that look to be along this line here, right, as I draw it here. All right, and we could see here, if we look at the vector 1, 2 and negative 2, 4, those themselves, u and v, one is a scalar multiple of the other. All right, so we could see that, well, if I do that, well, I'm really, what can I build? Well, we could see that if just given those two vectors, and really, I really just need one of them, right? I can build that line, right? Any vector that lies on that line, I could represent using vector u with a proper choice of scalar, whether it's going up in the positive direction or down towards the negative direction. So when we build, this is what we're talking about, right? The linear combination, what does that look like, right? Now, again, we're not always going to have a geometrical analogy here, right? Because we could do it in R2 and R3, right? But we're once we get to like R4, right, that this kind of like, there's no way to kind of visualize that properly here. But this is kind of, it's here to help us build our intuition for that, right? So now let's say that, right, I had another vector, right? Maybe still with u, but maybe now let's say our other vector is this a. Right? Vector a is this vector negative 3. So now we see here that this one is not along that same straight line that u was, like the previous one, and we can see it's not a scalar multiple. Right? And then we want to ask ourselves, well, what can I build with different linear combinations? Like, let's say 3a minus 2u. Right? Or negative a plus u, 2u, or let's call it 5u. Right? We have that there. Right? We could see here. So we could see two instances of different vectors that I can build, right? Now, what I want to ask myself is, well, is this enough to build the whole R2 space? Can I represent any vector on the plane here using just these two vectors? Right? And we will answer that question, right? But for now, we could see what can we build. Well, we could see we have these different sets of vectors, right? That we can build in the plane. All right, now let's look at here, R3 here. All right, and we'll take a look, same kind of analogy here, where here we have two vectors, u and v. Well, let's start with just u. All right, u, and then this vector w, or excuse me, b. Right, and we could see b is just a negative of u. All right, and we could see there that, right, they're pointed along different directions here. Right, one in the positive, the other in the negative. Right, but if I try to find any combination of u and b, let's say u minus b, right, what does that look like? We could see there, right? So again, what do these build? It looks like they build similar to the other. Let's call this one 3u plus 2b. And we could see here, actually that one got me back to the original. How about, let's call that 4b. 6b. There we go. All right. So we could see here, right, that those tend to lie when we're building what kind of object. It looks like it's just a line, right? And if we look here, I'll turn this one on. Now we could see what I graphed, what I've overlaid on there, excuse me, is just a line. We could see, let me, we could see the vector, our initial one u, and then we could see the line, right? So with the appropriately chosen scalar, I can make any vector along that line, right? So that is what we can build from this vector 1, 2, 3. Now let's say that here I have another vector v here. So again here, these are not on the line here. And now what do linear combinations of this look like? All right, so let's say we have u and v, so let's say about 3u minus v. All right, and we could see now this is different than before, right? Before they were on that line here, but now they're not, right? So how about negative 2u plus 3v? We could see that here, right? So now I have a different type of structure here, right? Now, before in R2, I asked, well, can we build the whole space out of this? Now here, institute one more here. How about 3u plus 5v. Now looking at this, it looks like I can't really build all of R3 here. It's a different structure that's getting built here, but since I am dealing with two vectors, similar to the previous example where I said, well, can we build the whole plane here? If we take a look at this, right, so what I plotted here is a plane. Now, if you look here, each one of those vectors, as you can see, kind of rotating it, they all live inside the plane, right? And as it turns out, using those vectors u and v, I can generate any vector that lies in that plane. All right, now not all vectors in R3 do lie in this plane, since plane is a two-dimensional object here, and R3 is three-dimensional space. As we can see here, there will be vectors All right, there you go. Okay, you could see here, sorry about the rotation of this thing. This vector W does not lie inside the plane. So I can build a lot of the vectors. Oh my God. In R3, but all of the vectors that I build lie on this particular plane, right? So, but not all of them do, right? So we do build a kind of structure that lives within R3 here, but I'm not able, at least with the set here that I've made up here of u and v, I don't have all of the vectors in R3, just a certain subset of them, right? Which we can see and then produce a plane. All right, now, what I've done so far, what vectors can these build? So the first question is this idea of a span, right? So the span is what's going to answer the first question. Okay, so the span is what vectors they can build, right? Now, are any vectors unnecessary? Now, that is going to be answered through this idea of linear independence. And we'll properly define both of these things in later videos. But these are at the heart of our topics for this week. Sorry, the pen is running slow here. All right. So those are the two topics here. And we can see some visuals here to kind of get us accustomed. When I say span, what am I doing? What's a linear combination? But we could see graphically here in R2 and R3 what that actually represents here. Okay.